Hello everyone and welcome back again. In this session we start looking on the grading of the aggregate. As we discussed before on the aggregates, and we have seen that majority of the concrete volume are coming from the aggregates, and that's why the aggregate property will strongly influence or affect the concrete property. And that's why we need to study and be more selective when we are using the aggregate in our concrete production. And one of the properties of the aggregate that we need to check and focus is the grading of the aggregate. So this is one of the properties of the aggregate. So we'll start discussing what is grading, how we do grading of the aggregates, and how aggregate grading will affect the concrete properties and the concrete mix design. So what is the grading? Grading of the aggregate, as we mentioned before, we have, for example, we have a fine aggregate and we have coarse aggregate. And normally the aggregate, if we are using, for example, the coarse aggregate, the coarse aggregate is the aggregate that has a particle size higher than 4.75 millimeter. So normally when it's using coarse aggregate, it come in a range. So the coarse aggregate, for example, in our mix design, we need to use a concrete that has an aggregate ranging and coarse aggregate ranging between 4.75 up to, for example, 20 millimeter. So this is how we are using aggregates. The coarse aggregate, it come in different range, and the minimum size of the coarse aggregate is 4.75. We don't use coarse aggregate lower than this particle size because the lower than 4.75 it's fine aggregate. It's a sand. We consider this is a sand, but the coarse aggregate has a minimum particle size of 4.75 millimeter. So what about the maximum size? So yes, all the particle size is higher than 4.75 millimeter, but what is the maximum size of the coarse aggregate? We have different selection or it based on the mix design. Different mix design of the concrete, they use different maximum size. So in this mix design, for example, I'm using 20 millimeter is the maximum particle size of the aggregate. So my coarse aggregate has a range between 4.75 and it can go up to 20 millimeter. In another mix design, I might use different maximum size. So in mix two or any other mix design, another mix, I can select the range of the coarse aggregate that is range between 4.75, which is the minimum particle size of the coarse aggregate, and can go up to 16 millimeter. This is the maximum particle size. It can go up to 16 millimeter, 14 millimeter, 20 millimeter. This is the maximum size of the particle size for our mix design, for example. So this is how we choose or how we use the coarse aggregate. The coarse aggregate come in different range, starting with the minimum particle size of 4.75 and it can go up to the maximum size of 14 millimeter. It can go up to the maximum size 20 millimeter range. So this is the range. That's how we can use the coarse aggregate. So this is first. Second, so I have this range. For example, if we are go as with an example that we are using concrete or coarse aggregate with a maximum size can go up to 20 millimeter. The minimum is 4.75 and can go up to 20 millimeter. So this is the range. In this range, we have four scenario for the particle size in between. Like this is, if we can say, this is aggregate 1, this is aggregate 2 or type 2, 3, and 4. And all of these scenarios, the aggregate particles are in the range between 4.75 up to 20 millimeter. For example, I have this particle size and all the particle size here, for example, let's say 16 millimeter. This one 16 millimeter. So 16 millimeter, it's still in the range between 4.75 and lower than 20 millimeter. 16 millimeter, this particle size, single particle size. 16, all the particle size has a 16 millimeter size, and 16 millimeter, yes, it is in the range between 4.75 and lower than 20 millimeter. So this is the first scenario, and it's applicable to be used as in this range. The second scenario that I'm using, for example, this is 5 millimeter. All the particle size is 5 millimeter, 555. So I'm using a particle size, single particle size of 5 millimeter, and it is still in the range between 4.75 and lower than 20 millimeter. So this is the same with this one. In this case, it is in the range. In this case, it's also in the range. The third scenario here, that I have a maximum size of 20 millimeter and lower, the minimum size is higher than 4.75. So and I have the existence of, for example, 5 millimeter. I have the millimeter here. Millimeter. I have the existence of, for example, 7 millimeter. I have the existence of 8 millimeter. I have the existence of 14 millimeter, 18 millimeter. So there is a good distribution of different particle size that lies in this range between 4.75 and 20 millimeter. So between 4.75, I have 5 millimeter particle size. I have 7 millimeter particle size. I have 8, 14, and 18 millimeter particle size, and all of them are in the range between 4.75 and lower than the maximum of 20 millimeter. So this is another scenarios that is applicable, and it is also in the range between 4 to up to 20 millimeter. Another scenario here that I might have a particle size of, for example, 5 millimeter, another 5 millimeter, 5 millimeter single here. I have also another particle size 16, 16, 16. So this one, we call it gap grading, aggregates. Sorry, this one we call it single graded aggregate, because we have only single particle size and it lies between these two range. In this range, also we have 555, still we can call it single graded, aggregate. This one, it has a good distribution. There is the existence of different particle size that lies between this range, between 4 up to 20. There is 18, 14, 8 particle, 7 particle size, 5 particle, the existence of this particle size. So this one we call it well graded, aggregate. This one that we have 555 and we have 16, 16, 16. So there is a gap here. There is a gap. We are missing the existence of the aggregate particle size between 5 to 16. So the total aggregate, it can be either 5 or 16. So there is a gap here. We are missing a gap between this one. So we call it gap graded aggregates. So, but in all of these 1, 2, 3, and 4, all of them, all of them are still the particle size range between 4.75 as a minimum and as a maximum of 20 millimeter. All of them has a particle size higher than 4.75, and all of them has a particle size lower than 20 millimeter. So the range, we might have different scenarios, different graded for the aggregate in this range. So this is what we call it, the grading of the aggregate. And this is very much important. We need to study what is our grading, our aggregate grading that we are using, and how these different grading will affect the concrete properties, because we know that aggregate occupy majority of the concrete volume, and the small change and the small, if they have any mistake or problem with the aggregate, it will strongly affect the concrete properties in general. So among different grading here, we need to use the well graded aggregates. It means that we need to use an aggregate in this range, and there is a good distribution of different particles in between. We don't need to use a single, whether all the particles are big or all the particles are small, or use either big or small and there is gap missing here. No, we need to use a well graded aggregate. It means we need to use an aggregate in this range, and there is a good distribution. There is the existence of the different particle size in between. Why? We will discuss why we need to be using this one. For example, here, this is how gap graded looks like, and this is how poorly graded or single graded looks like, and this is how well graded looks like. In concrete, we need to minimize the voids as much as we can. The less voids in the concrete body is the high quality of the concrete, and the high durable is the concrete. It's the good for fresh and the good for the hardening properties of the concrete. If we are using why do we need to use well graded aggregate? It means that there is a good distribution of the aggregate, small, big particles and smaller, big particles, smaller and smaller and smaller and smaller. Why? Because when you use we have using big particles here, and the smaller particle will come and lie here to fill these voids. Then we'll start to use another smaller that will lie and fit into this space, and the smaller will come and lie here to fit this space, and the smaller will come and lie to fit the smaller space, and the smaller will go further and fill on this space. So if we have a good distribution like big, smaller, 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 then we are trying to minimize, reduce the voids or the porosity of the concrete body. If we are using poorly graded or singly graded, can either all big or all small, then we have this one, and we'll have these spaces that we don't have any particles that can lie and fill these spaces. So in this way, if we are using a singly graded or poorly graded, it will maximize the existence of the voids in the mixtures. The same also go for the gap grading. We will still have also seeing some voids created inside the concrete body. And that's why we need to be selective and use a well graded aggregate that has the existence of big, smaller, smaller, smaller. There is a good distribution of the aggregate particles in the range that we are using. So we have here, for example, this is the aggregate. This is a big size, particle size. There is a smaller and smaller and smaller, 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 smaller. So there is a good distribution. This is the maximum and this is the minimum. And there is a good the existence of different sizes in between. We don't miss any sizes in between. The same of this one. We have a big particle, smaller and smaller, smaller and smaller. And here, how is the use of different grading of the aggregate? If we're using, for example, single size or single graded, and the gray color represent the voids, and this is how much is the voids, the sum of the voids that lies in between or created as a result of using a single size of the aggregate. If we're using poorly or gap graded, this is the amount of voids that's created as a result of using this one. But if we're using a well graded aggregate, means that we have a big, smaller, 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 smaller in this range, and it will be more compacted and less void. So compared to these different voids, we have lower, we try to minimize the voids and reduce the porosity of the of the concrete. The same here, and if we are using, here is single, also here single, here is well graded. If we are using the same container, same volume container, we're using single here, single, all big, all small, or we are using a well graded that we have the existence of big, small, 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 and we pour the water here. And the volume of the water to fill in this container is represent the volume of the voids inside the containers. And we can see here that this is the volume of water required to fill in the spaces, to fill the voids, and this is the amount of water to fill in, and this is the amount of water to fill in the voids. And we can see here the amount of water to fill this container is lower than the amount of water required to fill this one. It means that the voids in this container is lower compared to these two containers. Why? Because we are using a well-graded aggregates, and the well-graded aggregate means that there is a good distribution, and in this way we are trying to minimize the voids inside the mixtures. So this is simply what do we mean by grading, and we have different grading of the aggregates. We have either single graded or poorly graded, can be either all big or all small, or we can either big or small. So we have some missing here, we call it gap grading, or we have a good distribution between the big, small, and small, and small, and smaller. This one we call it well graded aggregate. So among different grading, we need to go with the well graded aggregate. Why? In order to minimize the voids inside the concrete. And as we said before, the more dense and the more compacted concrete, the less void, the lower porosity is the high quality and the good properties with the fresh or hardened properties. And so this is the first property of the aggregates. So aggregate occupy majority of the concrete volume, and we need to study the properties. We need to be more selective to use the aggregates. So one of the aggregate properties, the first aggregate properties that we are starting with is the grading of the aggregate. So grading will aggregate of the aggregate, it will affect the workability of the concrete, it will affect the strength of the concrete, the durability of the concrete, and etc. So we stop here and we'll see you in the following session.